So here's our first set of definitions that we're going to discuss in this class. Population. This is whatever you choose to study, and you can kind of define it. Now, a lot of times you can think of population of eligible voters in the United States, but it may be different subsets of that. It may be something else entirely. It doesn't matter. But the population is the complete collection of all of these things. It's every last individual that meets your definition or description of what's in the population or what the population is. So, emphasis on complete here. Now, in this country, every 10 years we conduct what's called a census. Now, what happens during the census? Does anyone know? Yeah, you get mailed letters, and if you don't fill it out, you get mailed more letters, and then more letters that get more threatening, etc. But basically, it's a law that every 10 years in this country we have to conduct a census, which means we have to, find out data from every individual in this population. Well, we're not as good as that as we might like to think. There's a lot of holes in our knowledge about our actual population. I mean, there's a lot of times you'll find lots of numbers on a website, etc., but they're filled in a little bit. They use statistical methods to kind of fill in the gaps. It's very difficult to find out information about everybody. And we realized during World War II, we realized that there were populations that weren't enumerated correctly. There was a lot more minority populations that showed up for the draft than we thought. So we were undercounting them. And they have good statistical methods that they can use to help improve the value of the census. But interestingly enough, Congress won't let them. Congress says, no, it's just a strict enumeration. Whoever shows up for the count, great, and then that's it. We can't use statistical methods to improve the actual numbers that we use for the census, even though we know what it is. Now, it's important to realize that the census is a collection of data from every element of the population. And even though we conduct a census, by the strict form of the word, it's not a census. It's a very good sample, because we're getting most of the people, but not all of them. A sample is when you're drawing from a sub-collection of your population. They don't get everybody. So if you're missing a few people, then it's no longer a census. So if I define as my population all the students in this room right now, and I collected information from just these first two rows, that would be a sample. It's not a census until I collect data from every last one of you. Now, why would you be collecting information? Typically because you want to know something. You want to know the average age, average height, average IQ, etc. And that number that you're looking for is a population parameter. This is a numerical measurement, or it's a number that describes some attribute of your population. The important thing to know about parameters is that this is sometimes kind of a theoretical value. I mean, you could calculate it if you had everybody, but it's this number that describes your entire population. You'd have to have information from everybody in order to come up with a population parameter. Typically what we get is a statistic. So if I just looked at the first two rows, calculated your average age, and said, well, average age here is, 20-something, and it said, well, that's probably close to the average age of the class, then what I'm calculating is a statistic, and what I'm hoping to get a good estimate of is the population parameter. So a statistic estimates the population parameter. Let's write that down. At least we hope our statistic is a good estimate of the population parameter. Sometimes it's hard, or sometimes it's impossible to actually know the population parameter. It's hard to know the average size of an adult great white shark. We just don't, you can't put them all in a big aquarium and then measure them. It's just impossible. But if you draw a lot of data, then you can get a sense of it by calculating a statistic. Let's look at a couple problems in the book that relate to statistic and parameters. So this is section 1.3. And the goal here is to decide whether or not what we're talking about, determine whether the given value is a statistic or a parameter. So we'll start with number 6. There are 50 state capitals in the United States. So 50, is that a statistic or a parameter? Parameter, because that's all of them, right? Problem number 8. Among the flights included in the sample of flight data in data set 15 of 15 of Appendix B, 21% arrived late. 21% arrived late. Yeah, that sounds like a statistic to me. You're talking about a sample of flights, so it's not all flights. So the number that you're going to get from a calculation based on sample data is a statistic. All right. If you don't know chemistry, then that's fine. You're not going to have to know chemistry, but if you do, that's great. The periodic table lists data about all the elements. The average mean atomic weight of all elements in the periodic table is 134.355 unified atomic mass units, or AMUs. Parameter, good. Because again, it's based on calculation from data that reflects all the elements in your population. So, good. So it was parameter, statistic, and then parameter for 6, 8, and 10, respectively. Now, the type of data that you collect has a lot of different names. And the first thing we're going to talk about is a distinction between discrete and continuous data. So we're going back to our handout here. Let's go through, these two. Discrete data. Oops. Discrete data results when you have a number of values that you could count. Now, theoretically, you can count quite high, but discrete data is data that has numbers that don't vary on a scale. That is, you can't have 3.5 TVs. You can't have 2.2 children, etc. These are going to be typically integer values. That's what we're going to typically mean when we're talking about discrete data. On the other hand, continuous data is something that can vary on a scale. Temperature is a good example of something that varies on a scale. Let's look at a few examples that highlight the difference between discrete and continuous data. Some problems 13 through 20 determine whether the data are from discrete or continuous data sets. problem number 14, I think I would have worded this a little bit different. All they say is that the Honda Civic has 4 cylinders. I guess to me the item in question here is the number of cylinders that a car has. What kind of data would that be? Yeah, discrete. All right, you can have 1, 2, 3, or 4, etc., but you can't have numbers in between. George Washington was 188 centimeters tall. I'd say that's continuous, right? You could be 188.5, 187.3, etc. You can be anything on a scale from some really, really low height to, I think, Robert, start with an L. There was a guy who was 8 feet 11 inches tall. It's the world record. Yeah, gargantuan. Just plant him in the lane and, man, he could block shots all day, right? Yeah, 8 feet 11. So you can be from really, really short to really, really tall. But it does, you can be anything in between. So it varies on a continuous scale. So in that one, I would say is continuous. And let's do one more, problem number 20. Down a little bit more, there we go. The circumference of a female arm. So in this case, it was 27.5. But in general, what do you think about this kind of data? Is it going to be discrete or continuous? Yeah, continuous. It can, again, it can be anything. You can just measure it more and more accurately, etc., and you can get as much precision as you want. So it's going to vary on a continuous scale. Good. Now within these categories of discrete and continuous, in particular continuous, there's going to be some more definitions that we're going to go through. Oops, let me zoom out a little bit. There we go. These 4 right here. One more. Nominal level of measurement. Basically, data that reflects names. So it could be categories, male and female, etc. But they're not necessarily things you would associate with a number. A lot of times people give them number values to input them into computers or spreadsheets, etc. But they're not necessarily things that would require a number. Maybe it's the color of your hair, etc. Ordinal data is a little bit different. Ordinal data are things that could be arranged in an order, but it doesn't necessarily make sense to subtract things within that. The first example that comes to mind would be your grade in a class. You could get an A, you could get a C, but it doesn't necessarily make sense to subtract the two. But you can put them in order. Perhaps a better one would be the quality of a blind date. Was it outstanding, or was this a person that, you know, has got a great personality, one of those, etc. So you can put them in an order from disaster to really, really outstanding, but it doesn't make sense to necessarily subtract them. By the way, the author has an interesting note on page 17 for men, and this is based on statistics. If you're going on, Tinder or Match.com, then for your photo, they found that it was optimal that you not look directly at the camera, nor should you smile. That'll make you somehow more attractive to women, I guess. I don't know. For women, let's not leave you out. Your best approach is to appear, and I don't know how you do this, you're to appear interesting, not sexy, which, I don't know. I'm just reading what the author said here, but I find that kind of interesting. And in your emails to each other, when you're introducing yourselves to each other, you want to keep them to about 40 words. That introductory email should be just about 40 words. So take that for what it's worth. All right. Well, let's take a look at a few things. We need to discuss one or two more. There's an interval level of measurement. So we're adding more structure to our types of data here. Interval levels. This is data in which it's meaningful to subtract the data. So today the high might be 57. Yesterday the high might have been 60. So you can subtract those and get a difference of 4. But what's difficult about Fahrenheit is that if it's 30 degrees tomorrow, I can't say it's half as warm as it was on Monday, because 0 on the Fahrenheit scale is not as cold as it gets. So it's a little bit tricky to deal with that. Now, if you want to be able to compare things and actually form ratios so that you can say something is twice as valuable as something else, or it's twice as cold, then you're going to have something in which 0 is a meaningful and real part of your scale. Now, not trying to make you physics majors, but that scale for us in terms of temperature is degrees Kelvin. Because 0 degrees Kelvin is as cold as it can get. I think it's like minus 476 degrees Fahrenheit. I'm not sure. I'm sure somebody could Google that for me real quick. But if it's 2 degrees Kelvin, and then it warms up to 4 degrees Kelvin, yeah, this is twice as warm. Although it's still going to be extremely cold. It does make sense to form the ratio of two things. So let's look at a couple examples for nominal, ordinal, and interval and ratio types of data. Let's see what we can make sense out of these things. We'll start with problem number 22. And again, our goal here is to try and decide what type of data that we've got here. So your choices, like I said, are nominal, meaning it's the data reflects kind of a name. Ordinal, there's some structure to it that you can put things in order, like grades or quality of a date. Interval, in which it makes sense to subtract things, but you don't have a nice form of 0. And then ratio, in which you can say something is twice as valuable or is twice as much as something else. So we'll start with problem number 22. The depths of earthquakes listed in data set 16 of Appendix B. Well, the depths are going to be in kilometers. Can I say that one earthquake was twice as deep as another? Does that make sense in this context? What kind of data would that reflect then? That'd be ratio. So that'd be ratio. Let's move down to the next one. The movie Avatar was given a 4-star rating on a scale of 5 stars. Could be nominal. Okay, Thad. We agree with nominal? Or is there... Could we also say ordinal? Can you order movies by their number of stars? Yeah. I mean, if Rotten Tomatoes gives it a 2 and another movie gets a 4, you can certainly put those in some kind of an order. So this one would be ordinal data. Car models. Nominal. Yeah, that's just a name here. So this would be nominal data. And by body temperatures in degrees Fahrenheit. Yeah, that'd be the interval. So you can subtract things here, but it doesn't necessarily make sense to say that one is twice as warm as another on this scale. So this would be interval. Those are going to take a little more practice. I would encourage you to make sure you don't skip these in your homework. They'll certainly be there. Let's do one or two more here. And I'm kind of going to veer a little bit off script. It says Dataset 15 Appendix B lists flight numbers of 48 different flights and the average mean of those flights. Well, let's just think about the flight number itself. What kind of data is the flight number? Yeah, it'd be nominal. It's just whatever they happen to choose for the name of the flight or the flight number. How about the length of time of that flight? What kind of data is that? It'd be interval, because certainly you can have flights that are twice as long as something else. Makes sense there. So actually it'd be ratio, right? It'd be ratio. So average here, the last one would be ratio. All right. We okay with these different levels of measurement? For homework, try problems 1 through 31. And that begins on page 21.